Okay, well, let's pick up where we left off with the accuracy and precision stuff, okay? I'm going to go into a little more detail with the precision today and some harder math as well. What we saw yesterday, Friday, what we saw was relatively simple stuff. Hardest calculation you had here was probably the simple percent error. And that causes problems. Let me tell you why. You're going to be doing a worksheet in about 15, 20 minutes when I'm done giving you the new notes here. What you don't finish, you have to finish for homework. But the problem I noticed as people were doing this, I think half the class got the first 3 questions, which were just percent error problems, wrong. And they were the 2 major mistakes I saw. I'll show them to you right now so you hopefully won't make them. All right, people don't bother to look at what these things mean. So, for example, let's say I told you, I gave you 2 numbers, all right? And I say the correct value, the accepted value in the experiment we're doing is going to be 10 grams per milliliter, whatever. And you measured it to be 9 grams per milliliter. People went and did a percent error on that. And they got answers like 90% error, that is. Now, does that make sense? You were supposed to get 10, you got 9. Does that look like it's 90% error? No. And that should be a dead giveaway. I have people who got 105% error for one of the answers. Okay? Clearly something's wrong if you're getting 105% error. All right? And you could get 105% error, absolutely. But if you see 2 numbers are right next to each other, they clearly aren't 105% apart, right? So you need to redo it. People were just leaving those answers down, no problem. All right, let's see the 2 big mistakes people made. Here's what they did. I said, okay, find the percent error if that's your observed and this is your accepted. So people said, okay, I looked back at my thing, I found my equation. All right, it's real easy. It's just going to be percent equals 9 over 10 times 100, and that's how they got 90% error. Is it 9 over 10 times 100? That's what a lot of people did because they didn't bother to look up what EA meant. EA doesn't mean one of those numbers or the observed. It means the observed minus the accepted. Or the accepted minus the observed. It doesn't matter because it's the absolute value of it, right? So you have to subtract them first. That was the first thing people were doing wrong. Don't do that. Second thing people were doing wrong, forgetting the times by 100. So they were getting, instead of, it should get 10% error, they were getting 0.1% error. Okay, so the 2 possible mistakes, getting ridiculously large or ridiculously small percent errors. Now, you don't need to write any of this down because it's already in your notes. The problem is, when you look back at your notes, you actually have to read what it means. EA is not observed. It's the absolute error, the difference between the 2. Okay, so that's the stuff with this guy. And that guy measures, as you all know, accuracy. Now, we're going to spend today finishing up this chart, which we started on Friday. And this measures precision. Let's talk about this chart a little bit. Everybody got this much done yesterday, right? Friday, we all got it done in class together, right? Okay. That was pretty easy. All you had to do, you found your mean was 10. You simply took each of these numbers, 10, and I'm leaving out the units. You cannot. You got to keep units and everything. I'm just doing it really fast today. Yesterday, I did keep the units. 10 minus 10 equals 0. 12 minus 10 equals 2, and so on. And eventually, you got the average deviation down here. And your average deviation, I think, was 1.2 for this guy. Well, you actually find that this average deviation of 1.2 grams per milliliter is not a very useful number. It doesn't tell me much. I've got to find something called the standard deviation. That's what this last column is for. And we're going to come back to this in a little bit after I explain what standard deviation is. Just like with percent error was way better than absolute error. Absolute error just told you the difference between 2 numbers. Percent error tells you how much they differed by, the percentage by which they're different. Well, the same thing is true for precision. The average deviation just doesn't tell you much, but the standard deviation tells you a lot. Let's talk about that, okay? You have those, you're still taking a few notes here. I gave you those 2 papers so you wouldn't have to draw all these pictures and write everything down. You do have to write a few things down. What is standard deviation? And by the way, there's 2 kinds, population and sample. I'll discuss those 2 as we're going along. Standard deviation measures how spread apart numbers are. Write that down. And you're picking up right off where you left your notes. We're going to come back and finish that chart in just a few minutes. But keep those papers I gave you handy. I want to show you what you're going to do with them. How many, in your class, there are like 2 or 3 people who were in stats class. Anybody in a statistics class in here? Anybody had one? Okay, there were only 2 in there that were in the stats class. If you were, you'd be getting a real heads up here. You'd be doing something before Thatcher does it in his class. Way before, probably. Again, you should not be bound by, see multiple people bobbing their head up 5 times to copy that down. It measures how spread out a group of numbers are is a very short sentence that you could easily remember in your head if you just read it. All right. So this tells us it's not the definition. It's basically the definition of precision, the repeatability of an experiment. All right. What we have to do here, though, is for some reason we're going to do this crazy complicated formula, which I'll try to explain why we're doing it. We have to take what sounds like it's really going to be tough, the square root, God bless you, of the variance. That is the average square differences from the mean. Wow, that's ugly. What does that mean? And why are we doing it? So 2 things. How do we do it? And why are we doing it? That's what I want to try to go over today. And I'm going to have basically those papers are there for you. And they're the same pictures I'm going to show you up on here. Those papers are there to help you understand why we're doing it for the most part. I'm going to try to show you how we're doing it with the examples. We're going to do it today and tomorrow. The other class had a double today, so of course they did both papers today. You will just have one of them, and you probably won't finish it. What you don't finish, you have to finish for homework. Okay? All right. First of all, let's talk about the purpose of this. Oh, here's the equation. You don't have to write this. Actually, you know what? Write the equation down. Not all this. This is already on your paper. Write the equation down underneath where your notes are. Okay? And another word, or another way of writing the symbol for standard deviation is a little omega sign. It looks like that. Because we write that above. Sometimes write SD. Some people write omega, and it says an S. All right, but the equation's the same, and it looks ugly. You do not need to write all these the legend underneath this because that is on your paper. Okay? So you don't have to waste your time writing that. So either SD or S capital D or omega or S is the standard deviation. Let's look at what it is first, real quickly, and then I'll show you why we calculate it and what its purpose is. You may have heard of people using this before, and I'll explain where in a minute. But basically all this equation is saying is you're going to take the sum of each individual value minus the mean. Hey, we did that. That's why we had that chart a minute ago. Each individual value minus the mean, we did that. And we even took the average, but with something we're doing different. For some reason, we're squaring this and then taking a square root of it. What the heck? Why? What are we doing that for? I'll try to explain why on the next board. For now, let me show you what the information we get, why it's used. Many of you guys ask after a hard test and bad grades, you're going to curve it? You want to curve the test? And what you want is me to add points onto your score. You don't want me to curve it. Let me show you why. Here's what a curve would look like, okay, for your scores on a test. You might say, well, okay, I'm okay with that. Really? Let me explain how a curve works. And I actually had one professor in college, who actually graded every single test on a curve. Here's what it would mean. It would mean that every single test, regardless of what the mean is, regardless of what the average of the test is, in your class, averages are always high. It's an honors class, right? AP class, honors classes, very high average. I think your last test, your average is probably around a 90 or a 91. So regardless of what the mean is, this many people and this many people only get an A. This many people fail. These are B's. These in here are C's. And this is a D. You say, well, I'm okay with that. Really? You'd be okay with a C? Your grade would be a C with a 91. Or even a little bit higher than that. Okay? That's grading on a curve. Grading on a curve, you have this what's called a normal distribution of grades. Okay? Where you have 5% of, or 2 standard deviations outside of the mean. And these guys in the middle and 1 standard deviation are going to be your C, there's your B, and there's your D. There are people who would do that. I don't, obviously, and very few people left nowadays grade like this. And would you want me to grade like that? Of course not. I mean, I think the lowest grade in the last test, I think I had 1 person who got in the 70s, I think, or maybe 2 out of 40-some people, right? Well, that means Fs would have been like 83s, and the 84s would have been an F. So you can't do that. Well, if you say we're going to grade on the curve from the beginning of the year forever, then yeah, you can. I mean, you might get a professor who still does that, but it's rare anymore. It's rare to see that. So you don't really want me to curve your grades. That's what I'm getting at here. So what is it about this standard deviation that we actually find useful? Well, we do find it useful for a lot of things. We find it useful for predicting things, even in medicine. We find it useful for analyzing our data in an experiment, and even for tests, especially for tests. We get the idea of how well people did based on their standard deviation and where it is. Let me show you another picture of it here. Basically, here's what it means. If you are within 2 standard deviations of the mean, okay, 1 standard deviation above, 2 standard deviations above, and then 1 and 2 below. If you're within 2 standard deviations of the mean, you are in 95 percentile. You're basically 95% of the people will do that. The scores will fall there. So a lot of things that fall like that. If I were to get the height in a large population like this building, like this whole school, I would find. Wouldn't I find something that looks like that for height? Sure, I would. Most people are going to be at the average height for men. Most people are going to be average height for women. A very small percentage will be up here. A very small percentage will be very short down there. Right? So there's a lot of things that fall into this kind of a distribution. So it's useful to classify things this way. All right? My question to you is, why do we now mathematically, why are we going to have to do this? And that's what I want to get to in a minute. But first, let's get to the calculation. Here's my dogs. That's mine. That's Buddy over there. There's Buddy. Buddy boy. It looks like Buddy. It's not really Buddy. Buddy doesn't have the pug kind of face that a Boston Terrier has, but it's a little longer because he's not a purebred. But anyway, all right, let's say I wanted to get the average height of this population of dogs. And this is all I cared about, was just these 1, 2, 3, 4, 5 dogs, right? I wanted to know what their average height was. Well, I could find that out. The average height, I would simply take all their heights at the shoulders in whatever this is, centimeters, I don't know, millimeters. Whatever their height is at the shoulders, I would take that, and I would get that average. The average comes out to be 394. Now, you don't have to write this down. That's why I did all this for you, so you could just follow along and show you how we do a standard deviation. Okay, so there they are. There are all there's my mean. See, well, that's nice. That's a useful number, but I wanted to know how small, how short a really short dog is, how tall a really tall dog is. I want to do the standard deviation for these guys. So what I'll do is I'll find the differences from the mean for each guy. Okay, so this really tall guy, he's 206 millimeters higher, or centimeters, whatever. This guy's 76 millimeters higher. He's 224 lower, 36 higher, 94 lower. Okay? Now, those are the deviations. We've already calculated that. We did that on the sheet, on your notes, just Friday. Okay? What are we going to do next? Let me show you. Then you've got to take all those values and square each one of them. Divide by how many samples you had, 5, and that gives you what's called your variance. It's called the variance. So instead of just taking them and dividing by 5, I square them first. So why do you want to do that? And then go and take the square root of that again to get your actual standard deviation. What's the point of that? Let me show you the point of that. Okay? Let's look at 2 values, 2 data sets. Okay? Why square the difference here? And by the way, all of this is explained better in the 3 pages I've given you there. You don't have to look over them now. Just watch up here. Here's why we do it. Which of these 2 number sets do you think has a better precision? What would you say has the better precision? Which one's less randomly spread out? This guy over here, right? You got 2 that are above and 2 that are below. That's not as random or as dispersed as this guy over here, which just seems completely random, right? Now, here's the problem. If you take the average deviation of both of these, guess what it comes out to be? Exactly the same. Average deviation for both of those comes out to be exactly the same if you don't square them first. If I square them first, I don't get exactly the same average deviation. As a matter of fact, I get the better deviation is the one you'd expect, this guy over here, versus the other guy, which I accidentally advanced the board. Okay? So the main reason is, if I square these guys, the standard deviation is a more useful tool, just like percent error is a more useful way of telling how far apart from the accepted value we are. Standard deviation is a more useful way of telling how spread apart our data is than average deviation is. Okay, we use it in a lot of places. And you don't know exactly where yet. I'm not going to get into that till tomorrow, and even then, I'm only going to cover the very, very basics. If you take a stats class, you'll learn. And if you go into STEM, and you guys go into the STEM program, you're going to learn from Mr. Gunther and Mr. Thatcher why we have to know how to do standard deviations when analyzing our data. We have to know if it's significant or not. We're going to be doing a lot of labs in this chapter and in the next chapter. When we get data, I got to know if it means something or if it's just random noise in the system, okay? All right. Now, the last thing I got to tell you here, you need to write this down. It should not be Roman numeral 2, I don't think. It should just be like underneath where we leave population standard deviation, right? It's not a Roman numeral. I'm sorry. It should not be a Roman numeral. Just write this down underneath this guy. What was the population one? What number was he? 2. So we just call this guy 3 then, I guess. I don't know why I have it. Actually, I do know why. I changed these notes when I was doing this in AP last year. So I forgot to change that guy. Now, a sample standard deviation is actually much more useful for what we do most of the time in chemistry. Because I don't have the entire population. All right, again, I'm almost done. Just hang with me for a few more seconds. Then we're going to start doing our some of these so you understand where I'm going with this and how to do it. That's all you really care about, I know. In science, we generally are taking a sample. All right. For example, I will give you 2 orange juices. I will give you 2 Tums and a Rolaids. I will give you 2. The one we're going to do in this chapter, popcorn. We're going to take Orville popcorn, and we're going to take a generic popcorn. Now, I'm not taking every single popcorn kernel of Orville or every single generic popcorn ever made. Okay? I'm just taking a sample. I went to the store. I happened to buy this package. There are tons more packages of Orville Redenbacher popcorn around. All right? So I'm taking a sample out. So I have to do something different with my calculation. It's a very small difference. But the reason we're doing it is this. If I get your standard deviation of everybody in this class, it's everybody in the class. It's absolutely all 20 people, 30 people, however many people are in the class, it's every one of you. But if I'm only taking a sample and I'm trying to apply it to the population, a larger population, then I have to do this. If I'm only testing a sample of an entire population, I'm going to have to subtract away 1 number from the degrees of freedom. That is the n value in the bottom denominator, the denominator that you were doing before. In other words, when you do your mean, instead of dividing by 5 in the previous example, we're going to divide by 4 because we're not as certain of our answer, basically. Okay, so write all that down, and then we're going to go and try it. I'll write the equation down as well, and then we're going to actually apply it to that previous problem we had a little while ago, Friday. So after you copy that, there's your equation. That's the new equation. Notice it's almost the same thing, except for n minus 1. It's the only difference. So write that down there underneath the sample population, the sample standard deviation. Now, there's a lot of stuff, and it looks like really, really hard math, but you shouldn't get too panicked yet. Because I'm going to do one with you. We'll do one together. And then I have a worksheet for you to practice this on. Okay, so the only difference here, you don't have to worry this I before it. Just sum of x minus x. What's x with a bar over? What does that mean? You guys know?
The average.
It's the average, the mean, right? The mean or the average. And there's a number of samples in the trial, how many times you did it, minus 1, and that's the standard deviation. It's another name for standard deviation. All right, let's practice this with the example we had. You're going to go back down to the top of your paper, or whatever paper that was on, where you had this graph, this chart, I mean. Where is he? No, I don't want it. Sorry. Right here. This chart right here. Okay? Right? Previous page. Now, you've already filled in a good portion of this, correct? You all got, when you did this, again, I'm not going to redo it for everybody, but I believe, well, it's pretty easy. We got 0, 2, 2, 1, and 1. Right? Guess what I have to do now? What do you think d squared probably means? You're going to square each of those numbers. Go ahead. Do that quickly. Oh, by the way, I know some of you, I didn't tell you to bring calculators yet. So Who needs a calculator? I'll pass them out. You guys do need to get some calculators. If you have your own, get them. But I'll get you some. Step back. Okay, so square these. Get used to using your own calculator. If you don't have one, this is empty. Something like that. What's that? There you go. Now, do we really need a I say, well, do I really need a calculator for this part of it? No. What we got to get here? 0, 4, 4, 1, and 1, right? Okay, we really don't need one yet, but you're going to need one, obviously, in a little bit. All right. Now, what do I have to do to get the actual standard deviation? Okay, that's what I want to show you over here. Hold on. Okay? All right, now, those are the d squared. Let's go. Now, I've got to show my equation. The equation for the standard deviation is going to be basically the square root of well, you already know these numbers, right? Basically d squared, the deviation squared, over n minus 1. Okay? I'm using d squared because we've already done them over there, right? All right. So basically, what's the sum of all those added together? It's the sum of that. We're going to have 4, 8, 10. Square root of 10 over, what do we have? Over what? 4, right?
What makes you do 10?
I add 10 because 4, and you add them all up. It's the sum, this little e sign in the equation. This is an e sign. Basically means the sum of all the deviations. Okay? Got it?
Yeah.
So 10 over 4 is what? Yeah, question?
If we did like 10 trials, would it be 9
Yes,
instead of 4?
if you do over 9, exactly. Exactly. So however many trials you have, you're simply subtracting 1 away when you're doing a sample. Yeah. So 10 over 4, now you need your calculators. All right, so 10 divided by 4 is what? And then take the square root of that. Do you guys know how to do it? Look on your calculator so you can figure it out. 10 divided by 4 will be 2.5, right? What's the square root of 2.5?
1.58.
What is it?
1.58.
Does anybody else get? I don't know. I'm assuming that's.
Why don't you square root 10 though?
I take the square root. I do what's under the radical sign
Right,
first.
it's
10 divided by 4. 10 divided by 4. 10 I got from these guys right here. I added them up.
You have to square that?
I did. Each one of these is squared already.
Oh,
We've already done that. That's why I did the chart first.
I'm sorry.
We've already done that. So 10 divided by 4 is 2.5. Square root is, again, make sure all of you do it because I don't know. Is it 1.58?
Yeah.
All right. So that's your standard deviation. Now, what that tells you when you're all done here, okay? Let's try this one again.
It's fine. Just throw it to the side.
Yeah, just put it aside. So what that tells you is, my mean over here was 10. All right? Grams per milliliter. By the way, you should always keep your units. I'm not because we already did these, and I did keep them that day. So I'm saying I think my answer is 10 grams per milliliter. But I could be off by 1.58 grams per milliliter, higher or lower. That will be one standard deviation. And I'd be 95% sure it would fall within 2 standard deviations of that. Okay? So in other words, like, well, assume that 1.5 is about 2 times that is about 3. I'd be sure, pretty darn sure, that my correct answer should fall between 7 and 13. Okay? Because 2 standard deviations below would be about 7. 2 standard deviations above would be about 13, right? Okay? That's what I would be saying in my answer. That's what I think my answer is, but I could be off by that much, and it wouldn't surprise me. It wouldn't surprise me a bit. Okay? 95% should fall in that area. And that's basically all you have to do for these calculations. Now, I'm going to have you practice that, but let me erase all this for right now. Your first 3 problems on this worksheet, they're just easy ones like this. First 3 problems on this worksheet are just like this. Don't forget what I warned you about just a few minutes ago, right? Do EA. Don't forget to multiply by 100. Oh, and one last thing. Don't forget to keep your units. All along, keep your units. We are going to learn where to round off starting tomorrow. But for now, all you got to do for rounding off for today, and probably for the today only, you're going to round your answers off to just 2 decimal places. After this, we're going to learn about significant figures and where to round everything off.